So hello there and welcome to another tutorial. My name is Tanmay Bakshi and today we're going to be talking about the Hierarchical Reasoning Model, which is a brand new architecture released just about a week or 2 weeks ago. And it's actually really interesting because in my opinion, it's one of the only really exciting machine learning papers I've read in a very, very long time. A lot of machine learning research these days is focused all around LLMs in particular. HRM breaks that cycle a little bit and it's a genuinely interesting new model in the world of reasoning. And the term reasoning in particular is one of the reasons it was hyped up a bunch when it was initially released. However, even though that's typically a signal for research that's not super fundamentally groundbreaking, I can in fact say that this is a very exciting set of discoveries. At least I learned a lot from this new architecture, and I'm really happy to be diving into it. The hierarchical reasoning model allows very small neural network models, at least compared to the ones that they're sort of being contrasted to learn how to solve really complex problems that require a kind of quote-unquote reasoning. In this particular case, I'd even say that reasoning may be better said by a word like search, for example. It's a really good way of applying neural networks to solve problems that require a kind of search inside of a solution space where you can't just immediately inductively find some sort of obvious solution. In particular, today we're going to be taking a look at how you can use HRM, this specific architecture and training regime, to train a model that can play Sudoku games. So given a partially filled out board, it'll predict what the unfilled squares values should be in order to win the game. Now, the way that the HRM works is by leveraging a couple different components, but at its core, the actual model architecture is actually pretty familiar. It's pretty typical. It's a transformer architecture. In fact, it's actually not even particularly deep. It's only 4 layers deep, well, technically 8 layers depending on how you count, because there's supposed to be 2 of these transformer modules working together. Even the fact that they are transformers is also an implementation detail, though. You could really be using any kind of model architecture here, but in the particular example the paper gave, and the example we're going to take a look at today, we use a transformer architecture. So there are 2 different modules to the HRM. Both of these modules have 4 layers each, and the way that they get the HRM models, or these modules, to solve complex problems like Sudoku is by repeatedly applying these 4 layers on top of the same states over and over again, allowing those layers to iteratively refine their results, and instead of having to have one really big stack of tons of separate transformer layers. Now, typically when you're dealing with neural networks like transformers, in order to get them to solve more computationally complex problems, you need to stack more and more layers on top of each other. Now, again, this is not 100% accurate because technically universal function approximation theorem means that you could just scale width. You keep going and eventually get the same result, but in practice, you need really, really deep models to solve super complex problems. But when it comes to something like Sudoku, you don't need tons of independent layers that are learning their own weights and inflating your model size, because you're applying the same algorithm just iteratively. You're backtracking, for example, you're searching. And so you could 100%, in theory, use the same, say, for example, layers to solve the problem just repeatedly applied in a way where you're optimizing for them to refine towards a certain output. And the way that the HRM does it is by having, as I mentioned, these 2 separate modules. They call them the high-level and the low-level reasoning modules. These 2 modules operate at different time scales. It's somewhat biologically inspired, similar to how your brain has different parts that will operate at different frequencies, operate at different time scales. The H, or high-level, and L, or low-level modules in the HRM also perform this similar kind of communication. When provided with input, the low-level reasoning module will update very frequently, and only every, say, t number of steps will it then update the hidden state of the high-level module, which will then influence the state of the low-level module again, and after a certain number of iterations of both this high and low-level module, you take your final hidden states and you make a prediction. Now, on the surface level, this doesn't seem too particularly advanced, but there are a couple tricks that the HRM paper introduces that actually makes this both feasible and also solve some problems that a lot of typical approaches would have if you were to try and implement a model like this. And one of the issues that you'd face is that if you didn't have these 2 separate modules operating at different timescales, then typically, if you were to just take the same block of layers and apply it to the same states over and over again, you'd be using backpropagation through time in order to optimize those weights, because you're applying the same ones over and over. However, with BPTT, optimization is usually heavily focused towards the initial couple of time steps. because it's focused towards the initial couple of time steps, and because the gradient sort of vanishes or gets noisier at the very least towards later time steps, that means that you eventually end up finding weights. You find a minimum in your weight space, where the model will converge the hidden state very early on through those series of applications that you would have of your layers. So if you're applying your layers, say 100 times, as an example, it's very likely that your optimizer will just help you find weights where the hidden state effectively reaches or converges to some fixed point in the first couple time steps, and then it doesn't really change after that, even though you continue to apply your layers. And this means that you've effectively reached this state where your residual stream isn't being updated anymore, and so even though you're applying it 100 times, you're effectively only applying it something like 10 times. And this is just an inherent limitation of backpropagation through time in the way that we optimize these models. Additionally, it's also very memory intensive. And the authors argue that the fact that it's so memory intensive and the fact that you have to have this entire history of the rollouts of all these different applications of your layers means that it's also probably not very biologically plausible either that your brain does something similar. And so with HRM, first of all, having these two separate modules, high level and low level, where the high level module is only sometimes updated every couple of iterations, as well as having that high level module then go back and influence or update the low level module states, means that effectively what we're doing is we're allowing that low level module to reach some sort of local equilibrium point, but then the high level module kicks in and changes the hidden state for that lower level module, putting it in a different space, enabling it to then sort of contract that point back to where it wants to converge it to, by which point the high level module is able to shift it again and then allow the low level module to converge, and so on and so forth. That's the first major sort of insight from this paper. The second one is that if we are expecting this model to have this behavior of converging to a fixed point anyway, that actually means that it's 100% feasible and is 100% a good approximation of the true gradient to not even do backpropagation through time at all, and to instead only respect the gradient from the very last step of that entire application procedure. And so of all the time steps of applying the low and high level reasoning modules, you could actually just take a look at the gradient of applying the low and high level modules one last time at the very end and completely treat the rest of that stack of computations as a constant, and the gradient you get from that is apparently a good enough approximation that you will eventually train the network to converge to a good solution. It's really interesting, and to me at least was very unintuitive, but when you take a look at the math, it does in fact check out. And finally, one third really important part about the HRM architecture is that it has what's called adaptive computation time built in. It has a specific output head that uses Q-learning to predict when the model should halt, when it's reached a state that it's solved the problem in, enabling you to, at inference time, then only run the model for a certain number of iterations, where that number of iterations is in fact what you expect to run, or what you need to run, where the model believes it's now solved the problem. All in all, this enables an architecture that scales well past what you do during training. So for example, you can train it on simpler problems and then inference on harder problems and use more of these computation steps because you've learned this generalized architecture that iteratively refines its own belief of what the solution is, and you can solve more complex problems at inference than it saw at training. It really is a fascinating generalizable architecture. On top of all of that, HRM, today the example that we're going to be taking a look at is implemented in MLX, and it's an end-to-end example that you can train on your own computer as well and run inference with. And so now, without any further ado, let's go ahead and take a look at how HRM actually works and how you can train your own. Alright, so we're going to start off with the most boring part of the code. As you can see, I've got the HRM ACT model config here. HRM ACT stands for Hierarchical Reasoning Model Adaptive Computation Time Model. So it's a bit of a mouthful, but this configuration gives us all the different parameters we need to actually instantiate the model and deal with its runtime. Moving on from that, because we'll see where the parameters are used, comes the HRM ACT block. This is actually a very vanilla transformer encoder block. All it does is it stitches together self-attention and a multi-layer perceptron together with post-norm. So the norm is applied after the residual connection. And we use root mean square norm, so it's not as heavyweight as layer norm. This follows what the authors of the paper did as well. Past that, we've got the HRM ACT Reasoner module. The Reasoner module is a pretty standard stack of transformer encoder modules, so typically this would be called just a transformer encoder. The only slightly different thing about it is, if you remember, we're almost treating our transformer models, these modules here, the low and high level modules, as a kind of recurrent cell. And so as a recurrent cell, they need to be able to take two inputs. The inputs being their current hidden state, as well as an input injection to apply at that time step. It's just that in this case, it's not really a time step as much as it is a compute step. And then they return their next hidden state. And so for now, the way that this module does it is it just does an element-wise addition of both its current hidden state as well as the new input injection. The authors of the paper do mention that there may be better ways of doing this, but that figuring out better ways of combining the inputs is separate work. For now, this works well enough, although we could get better performance if we were to have a smarter way of combining the hidden state and the input injection at any time step. Past that, we finally get to the more interesting part of the code, which is HRM ACT inner. The inner piece here is really what ties everything together. It's what actually contains both the high and low level reasoning modules. We start off with a submodule type within HRM ACT inner. This submodule is really just meant to hold two arrays, and these two arrays represent the initial hidden states of both the high and low level modules. Now, the reason it's done this way is because the authors initialize these randomly in the beginning, and this is a bit unorthodox. I mean, whenever I've trained recurrent neural nets, we usually either start off with the initial hidden states being all zeros, or with the initial hidden states being a learned parameter. I've never done it this way where it's a randomly initialized initial hidden state, but then it's also frozen, so it never changes. It's just those are the starting points that we happen to have for the model, but it does seem to work, so we're following what the authors did. And then past that module exists a structure that just holds the two initial hidden states, or really any pair of hidden states, together. This module, once again, is meant to actually hold the initial ones. This structure is meant to just hold two hidden states together. Could be the initial ones, could be future ones at a certain time step as well. Past that, we've also got the output of the HRM ACT inner. This is special because, again, we actually have to hold multiple outputs. It's not just, the next hidden states. When we run through both the high and low level modules, we get the new hidden states, but then we also get an output prediction. And this is effectively what we use as our prediction of what the values should be for the unfilled squares in the Sudoku board. And we also have the predictions for the Q-learning head that's performing the prediction of should we halt and stop evaluation, or should we continue? Have we not solved the problem yet? Do we need to run more evaluations of the neural net before we can actually call the problem solved? Past that, I think we can skip through a lot of this initialization as it's very vanilla, transformer initialization logic. There's nothing here that's particularly special. The only thing to keep in mind is that, again, we are initializing both the high-level reasoner and the low-level reasoner modules. And these have the exact same initializations, the same width and depth and so on. It's just that this one is the one that we're going to invoke a bunch of times fast, sort of like higher frequency. This is the one that we invoke slowly to enable it to set the low-level reasoner on these new compute trajectories. And then finally, we get to the part of the logic that implements the actual forward pass for the HRM. Now, right off the bat, the two inputs that we take are the current hidden states for the modules, as well as the inputs to apply. The inputs to apply, in our case, would be discrete tokens for the Sudoku board. So these would be integer indices of the actual, sort of token vocabulary that we want to feed from the boards that we're currently running through the model. We then go ahead and run those tokens through an embedding layer to turn them into vectors, and we also stack together a bunch of CLS tokens at the beginning of the sequences, turning each sequence in the batch to an 82-long sequence, where the first token, of course, is a CLS token, typical to transformers. The remaining 81 are the 9x9 boards tokens. From there, we run through our cycles. This is the fun part. This is where we actually call the low and high level reasoners. Both of those reasoners have their own predetermined number of cycles that we know we want to run based off of the config. However, we don't run all of the cycles. We actually run one less than we expect, and I'll show you why in just a moment. For each one, we start off by invoking the low-level reasoner. It has its own hidden state, of course, and its output is what we update that hidden state to. So for each of these cycles, we pass it its own hidden state, which then gives us the new hidden state, which then gets passed in the next iteration, and so on. This is why you would typically need backpropagation through time. The input injection at every single time step is the same. It's simply the high-level Z, which is the high-level reasoner's hidden state, plus the input embeddings, which is the board state plus the CLS token. When we get that new contextualized hidden state, it's slightly refined of an idea of what the current state space is for this model and how it believes we should solve the problem. But if the cycle that we're at, modulo the number of low-level cycles, is 0, meaning we have reached the end of our set of low-level cycles, then what we do is we actually also invoke the high-level reasoner. So this is sort of what's slowing us down and preventing us from invoking the high-level reasoner every single time. It's for every one of the high-level cycles, which will perform T number of low-level cycles, right? So right as we reach that next iteration of the high-level module, we then invoke the high-level reasoner, give it its own hidden state, and its input is just the low-level hidden state, right? So we haven't actually even given it, technically, the board data directly. It's just viewing that low-level hidden state, which gives us a new high-level one. Going down from here, you can now see why we didn't run all the iterations. It's because at this point we have to stop the gradient for both of these hidden states, because this prevents us from doing backpropagation through time. By stopping the gradient at this point, future computation using those parameters is going to treat them as if they were constants. MLX, or any library that you use here, would not care about the fact that those values came through a bunch of computations that leverage parameters that we are computing the gradient with respect to. It stops that flow. From here, we can then simply run the same code we did up here just one more time, and this time we get the actual gradient to flow through the right parameters, but only for this single iteration. At which point we can simply say, hey, let's take all the tokens that had to do with the actual board state, which is the first, or I guess second onward, run that through our output head to create the logits, the probabilities for the different predicted tokens of what would be the correct outputs at whatever board or square indices. And then we can also perform our prediction for the Q-learning head, which is performing our adaptive computation time predictions. So that's based off of the CLS token, which pools together global information from across the board state. We can then construct our output, which consists of the hidden states for the high and low-level reasoners at the end, our output logits, and of course the logits from our Q-learning head as well, telling us whether we should halt or continue the computation. Now, one thing you'll notice in particular is that we once again stop the gradients when we pass the hidden states back to the caller. The reason for this is because even though there's a certain number of cycles that we're going to run here, there's another really interesting property about HRM training, and that is that HRM training doesn't just run a bunch of cycles within an individual step like this. Instead, what's going to happen here is HRM, its training loop logic actually allows us to take these high and low level states for an individual sample in the batch and carry them over to become the next initial hidden states for the next round, for the next step in training. So if, say, you've got 512 boards in your batch, it's actually possible that in the next step that you take in the training procedure, you might actually keep all 512 samples as they were before. You're optimizing the model again on the same training samples. The difference being this time, however, that instead of the model starting for each sample at the initial hidden states, this time the model would actually start on the hidden states that they ended on the last time. This is a bit unorthodox. I mean, first, right off the bat, you're training the model on samples it's already been trained on, but this almost acts as a kind of regularization mechanism, because the model is now seeing the same data, but it's starting at a different state. So it's enabling the model to take, for example, whatever work would have been done in the previous iteration and learn how to even further continuously refine these states and come up with even better predictions. The authors of the paper call this technique deep supervision, and it enables these quote-unquote different segments of work to be done across different steps. Now, probabilistically, so stochastically, there will be different samples that will eventually be dropped from the batch, and you can actually see that logic in the training code here where we define the loss function. So in fact, let's actually go through that now. So our loss function for the Sudoku problem in particular takes, of course, the model, hidden states, board inputs, board targets, segments, and a key. This is for random number generation. Now, what does segments do? What segments does is it keeps track as a simple integer value of how many times every individual sample in the batch has remained in the batch, like how many steps those samples have stuck around for. When they reach a certain maximum value, we will forcefully evict them regardless of whether the actual HRM model believes that it's time for us to halt. So right off the bat, we got to run the model and get our output. From our output, the simplest thing we can then do is determine the loss for the actual Sudoku predictions. So given the output logits, we can compute the softmax cross-entropy loss of those output logits against our targets, mask them to only the board inputs where we didn't specify the numbers. So effectively what this is doing is it's saying, hey, let's mask out the loss for any squares where we already gave the model the number so that we only consider optimizing the model on the squares where it had to make a prediction instead of just learning an identity function. We can then also compute an output accuracy value, and we can use that output accuracy to determine a target value for the Q-learning head of whether the ACT logic should halt. Because by definition, we're going to train the model to only ever predict that it needs to halt computation, meaning that the model should believe it's the last segment if it got every single square of a prediction correct. So if all the predicted squares are correct, then we will teach the ACT head to say, yep, it's time to halt. Otherwise, if there's anything wrong, it should not halt, it should continue computing. From there, we've got the logic that actually helps us determine whether or not any individual sample should be halted. At its core, what this is doing is it's checking simple conditions, like, for example, making sure that the next segment would not go over the maximum number of steps or segments that a sample is allowed to remain in the batch for. Combining that with a little bit more just random sampling logic to potentially keep samples around for longer than they need to be, just so that the model can be, used to working on a state where it is already solved, for example. We use that to determine finally as Boolean values whether or not any individual sample should be halted or should be evicted after this step. From there, we then have to compute the loss for the Q-learning or the ACT head. This is where things get a little bit more difficult, because we also have to figure out some sort of target for the continue head. What should the continue head's target be? Well, in this particular case, the way that it's done is by actually invoking the model yet again on these next hidden states and the same inputs. And by taking the halt and continue outputs from the next segment that we would have run on the next step. Of course, we have to stop gradients because we don't actually want to, again, do backpropagation through time here. But once we stop the gradients, we then go ahead and leverage some logic that the authors put in to determine which of these values to use as the target for the current continue head. If we are currently dealing with the last segment, so we are in fact on the last segment and we're going to be halting, then the target for continue is just the next halt value. However, if we're not on the last segment, if we believe that there is more work to be done, then whichever one of the next halt or continue values were greater is the target for continue, which we then use to compute a binary cross-entropy loss for the ACT head. We then compute our average losses and some auxiliary accuracy values, which are then returned from our loss function. So it's actually not that complex when you walk through it step by step, but it is definitely unorthodox. It's not a typical or standard loss function by any means. And then I've also got like a little abstraction here that enables me to do things like, for example, replace individual indices in the batch more easily. So for example, if say I determined that index number 4 out of a batch of size 512 has to be replaced, instead of writing that logic elsewhere in the code, I can simply call the replace function on the actual training batch, and it'll replace the value at that index. So once again, definitely unorthodox. I've also done something that the authors didn't specify in the paper, which is that I've enabled a kind of like curriculum learning here, where the model will actually graduate through different stages during training of how difficult the Sudoku boards are that it sees. It starts off very easy, enabling it to get like an initial understanding of the problem, and then it becomes a little bit harder and so on and so forth until it reaches the final grade of this curriculum, at which point we keep the difficulty distribution approximately the same. And then from there, just simple training step logic. The step function will simply define another function that gives us both the value and the gradient of invoking the model with our different inputs. And then given that, we perform an optimizer step on the model given the gradients, and we perform a print so we can see some logs. And finally, the interesting part I was talking about previously, we take that isHalted array that we computed in the loss function and use it to replace any halted samples inside the batch. This is then passed right back into our main piece of code here, the train function. The train function will of course instantiate the model, instantiate the optimizer, create our batch, and then from there, simply invoke that step function over and over again, adding some logging logic in and occasionally saving checkpoints. So every 250 steps, this will save a checkpoint to disk from wherever you call it from. And given those checkpoints, we can then load them back at inference time to actually test out the model. Additionally, this part of the code will deal with graduating if the model has reached a certain level of rolling accuracy. So over 300 steps, if we're consistently over 85% rolling accuracy of predicting blank squares, then we will simply graduate the batch up to the next level of the curriculum. And finally from there is our inference logic. Now, the way that I've set this up, when we invoke the code, we should be able to either choose between training or inference modes. I'll quickly walk through the inference logic here, and then we'll try them both out. So the inference logic is actually quite simple. It's effectively a single sample, so batch size of 1 variant, of what you just saw in that training loop, except this time we actually listen to the model instead of, for example, forcing it to stop computing or forcing it to continue computing despite wanting to halt. We start off by generating a Sudoku puzzle of a certain difficulty after we've loaded the model parameters. And then we can simply turn that puzzle into an MLX array so that we can feed it into the model, grab our initial hidden states, and then loop through every segment up until the maximum number of segments that were specified in the config. Now, we may arguably want to actually do more segments, as of course the authors of the paper determined that performance does in fact still scale at inference time going past the number of training segments. However, for now, for simplicity, because I haven't gotten checkpoints that are quite as good as the authors, we're going to halt it at the same number during training. And so from there, we invoke the model, grab our hidden states, see our predictions. All of this logic exists purely to print out what the prediction was, so translating those predicted logits back into like a Sudoku board form that we can actually print like so. So we print out what the current prediction is at that segment, take a look at our halting and continue probabilities, and if our halt value is greater than continue, we break. If not, we keep going until we reach the maximum number of segments. And so for each one of these prints of our current predicted board state, we actually log down how many of the squares were truly correct because we do already know the solution. And that way, at inference time, we can tell if the model got the problem, got its solution correct. So without any further ado, let's actually go ahead and try it out. Now, how about we start with the training logic? Of course, because I'm recording, I'm expecting this to be especially slow, and I'm not going to run this for too long, but you can, well, Apple Silicon's pretty good, I guess. It's faster than I expected, but yeah, as you can see, it is in fact training. So I'm going to stop that for just a moment. But as you can see, during the training process, we see a couple things logged. We see the cross-entropy loss and the current accuracy of that output head that's performing the predictions of the actual values to put in the Sudoku boards. There's the ACT head, which starts off actually with very low losses and 100% accuracy. And if you think about why that is, it's because we're only incentivizing the halt head to predict not to halt in the case, or rather to halt, in the case that the output was perfectly correct. So for the first many steps of training, this ACT head is always going to be perfect because it's never going to be predicting to halt because it's never correct. And so we are effectively allowing this thing for the first many hundreds, maybe thousands of steps of training to overfit to always predict never halt. Eventually, when the model starts getting enough of these correct that some of the boards are actually fully correct, then we're going to see this accuracy initially drop and then rise back up as the ACT head learns how to deal with actually having to predict whether we got the answers correct. We can also see how many puzzles we've gone through so far, because again, training here is not like, linear where every batch is a certain number of puzzles or a certain number of samples. They sort of like swap in and out dynamically based off of stochastic factors. So that's useful, and then we can also see our curriculum level from 0 to 4. And just like that, there's a training process for the HRM. So I actually already ran this training process so that you didn't need to watch paint dry, and I ran it for 17,000 steps. So I just set this thing to run overnight, and after a night of my max fans being really loud, it did in fact work. And now I've got this checkpoint that I can use with Inference. Let's start off with something that's really easy. So you can actually specify the difficulty level in the Inference script, and as you can see, it's basically instantaneous. We see both our puzzle and our prior known solution, and then given that, we can see the 2 segments of compute that the model performed. Keep in mind that we actually told the model that it could perform up to 16 segments of compute. However, it only actually did 2, because by the second segment, the halt value was greater than the continue value, so the model told us that we can actually stop computing early. As you can see in the first segment, the model got 34 out of the 35 squares correct, and finally, in segment 2, it got all 35 of the unfilled squares correct. Just like that. Now, how about we try with something a little bit more difficult? What if we went from very easy to easy? As you can see, similar situation here. We have our puzzle and solution, and then we see that the model performed 3 segments worth of compute. It started off with 33 out of 41, then 38 out of 41, and then 41 out of 41. And right as it got all the squares correct, it knew that it got them correct. Keep in mind that this metric here is not something the model's aware of. This is us telling ourselves that the model got 41 out of 41 unfilled squares correct because we happen to know the solution. But despite not having access to this ground truth metric, the model was able to predict that it got the answer correct and told us to stop computing 3 segments into the theoretical, training maximum of 16 segments. And we can keep going in terms of difficulty. If I run this on medium, as you can see, this time instead of 3, we got 4 segments. We started off with just 34 out of 49 unfilled squares being correct, and scrolling down, we see that eventually the model did in fact predict all 49. Now, past medium, things start to get a little bit more iffy. Hard, for example, I have seen it sometimes fail on, but in this case, as you can see, it did in fact work. So we get 53 out of 53 predicted squares after 5 segments, with this being our initial puzzle and solution. So as you can see, quite a few unfilled squares. And let's run hard maybe 1 or 2 more times. This time it got it in 3 segments. This time it failed. See, it didn't actually get it despite going through 16 segments, although there is a chance that if we kept going past 16, it would still be able to compute it. Although most of the times it's able to solve the hards. And finally, let's go ahead and try extreme difficulty. As you can see, our first extreme unfortunately didn't work. Second one didn't work either. Is the third time the charm? It wasn't. But if we keep running this, there we go, 4th time, I guess. The 4th time, it did in fact manage to predict all of the 56 unfilled squares in this extreme difficulty puzzle in 5 segments. And it knew when it did so, enabling us to stop computing. So here was our puzzle and our solution, and it managed to predict all 56 squares. And so just like that, we were able to train a hierarchical reasoning model in Swift. Of course, there is still work to be done. There is still parity work to be achieved to get it working with, for example, the extreme data set the authors set it up on. But at the end of the day, this is, as far as I can tell, a quite faithful implementation of the HRM architecture in MLX. And of course, all the code that I've been showing you here will be available down in the description below, as well as a JAX reimplementation of this in Python for those of you who want to run on NVIDIA GPUs or on Linux machines or Windows machines. Feel free to use that implementation as well. This was really exciting for me to work on. I love this HRM architecture. There's a lot to learn from it. And of course, I hope you enjoyed this tutorial as well. If you did, please do make sure to leave a like down below, leave a comment down below, or reach out to me over email or social media if you have any questions, suggestions, or feedback. I would love to hear from you. And of course, subscribe to the channel if you enjoyed, as it really does help out a lot. And turn on notifications so you're notified whenever I release videos just like this one today. And with that, thank you very much for joining. Goodbye.